everybody. We are going to talk about Loom and virtual threads. That's a feature that is still in a preview in the JDK 20, but as I'm going to explain you, it may make it as a final feature in the JDK 21. At least it's kind of on track for that, and we're going to talk about that. If you have questions during the talk, there are not that many people here, so just raise your hand, make some noise so that I can see you, and shout so that I can hear your question, and I'll gladly answer it during the talk. All right, so my name is Jose, and I was hoping that this guy would be working, and it's not. Okay. Not working. Here is a set of links with some content I like to publish on the internet, including YouTube and this kind of thing. I'm a member of the Java Developer Advocate team at Oracle. I joined the Java Platform Group 2 years ago after being a professor for 25 years at the university in Paris. Along with the JDK 17, that's not particularly new, but we did that a while ago. We published a new website called devs.java, where you can find, hopefully, all the information and the documentation you need about the Java platform. We have this Learn tab that you can see on the top left. That is where all the documentation is, and also community pages and this kind of thing. If you now want to connect with the team and see all the content we publish, you can go on YouTube and follow the Inside Java newscast by my friend Nikolai and Billy. I myself work on a program, on a series called the JEP Cafe that is very nice. And unfortunately, I don't have a cup here. That's the question that people keep asking about the JEP Cafe. We also have a podcast, if you don't like videos, called the Inside.java podcast. And if you don't like videos and if you don't like audio, you can also read with the content of Devs.java. And if you don't like to read, if you don't like to listen, and if you don't like to watch, well, I don't think there's much I can do for you. Maybe you should consider doing something. Okay, and we also have community pages about Java user groups and events all over the world called Java Days. We are doing a Java Day in Paris in June, and there are several Java Days organized all over the world. So you can also visit this page to see what's going on in that regard. Right. That's for the community part, and that's also for the podcast or Inside.java. Loom, as you may already know, is still a work in progress. So many things that I'm going to talk to you about are still under development. They may change before making it as a final feature in a JDK. Many things are not going to change that much, but still. Plus, if you have feedback, if you have questions, if you have comments, that's the right time to just talk about it, because many things are still being developed, considered, tested, debugged, etc. So that's the right time to provide comment and feedback. Loom is described in a number of JEPs. There are 3 of them. The first one is the JEP about virtual threads. That's the current state of the JEP. It doesn't have a number yet because it's still submitted. The status of this JEP is still submitted. But as you can see, it's not a preview feature. It's not virtual thread preview feature. Meaning that if this JEP makes it through the OpenJDK process, it will become a final feature of the JDK 21, which is awesome news, really. Just to give you an idea of the amount of work that Loom represents, that's a tweet that my friend David Delabasse did a while ago about the merging of the Loom features in the main JDK branch. All right? So you can see there are close to 100,000 lines of code that have been modified. That's one pull request. You know what a pull request is? Yeah? You know what code review is? When you want to merge a pull request, you do a code review before that. Okay? So there are people actually who did the code review for this pull request, and people who merged it in the main branch. It took about 10 days to do, which is not bad. That means that they did 10,000 lines a day, which is a lot actually, which is pretty fast. So that just gives you an idea of the size of the project and probably one of the reasons why it took about 4 or 5 years to develop the project and to bring it as a preview feature in the Open JDK. There is a second part in Loom called the Structured Concurrency. The Structured Concurrency, that's the JEP 428 in the JDK 20, and this is the incubator. This is an incubator feature. The main difference between incubator feature and preview feature is that all the classes available in an incubator feature are under a package named jdk.incubator.something, here concurrent, because that's concurrent programming. Okay, where a preview feature, the package will not change. It's the name of the package is probably the final one. So if you're using an incubator feature in your production code, which you can, by the way, you need to know that when it makes it as a final feature, you will have to at least update the imports, the import lines in your source code. So that's for the structured concurrency. And the last element that Loom is bringing is the scope values, which is also an incubator feature. And scope values are meant to be a replacement of thread local variables. Okay, many people are using thread local variables. That's something that has been designed 25 years ago. Do you know that there is a remove method on thread local? Yeah? Okay, no one? Great. So if you never call remove on your thread local variable, it means that it sits there for the life cycle of your application and that anybody can read it. So if you put some kind of security secret in your thread local variables and you never call remove, that's probably a security breach you may want to look into. Okay. There are already a number of elements that have been delivered as final features in the JDK 20 in Loom. These first elements are methods in the thread class, the future interface, and also the executor service. It's mostly, I would say, cosmetics, syntactic triggers, not the revolution, but it means that Loom has already been the occasion to modify the JDK, and probably for very good elements. All right. If you want to know more, if you want to give feedback, if you want to be really on the edge of things and get the latest information you can get on Loom, that's the only URL you need to follow and to connect to. There is all the documentation, the early access versions, the mailing lists, everything you need to know to really follow closely the development of Loom. So the first preview features of Loom were published about a year ago. Yes, actually even a little more than a year ago. And the adoption is already there. Absolutely all the frameworks you can think of are in a process or have already adopted Loom as a preview feature and are ready to be updated once Loom make it as a final feature. Okay, you have Tomcat, you have Spring, Vertex, Quarkus, JT, Spring Boot, etc. Elidon. All these projects are already, I would say, Loom ready. Okay, and Loom is not a final feature yet, so that's a good sign. I would like to put things in a perspective because I like to do that, and also to make you understand that Loom is not something that has been created out of thin air. It comes here, and it's here to solve problems we have in concurrent programming. So Java was one of the first languages 25 years ago to actually have a concurrent programming model baked in the language. So as of Java 1, you can create threads. You have a model for task which is runnable, and you can run a task in another thread launched by the main thread. The book you need to read is this one. You can still find it. That's the second edition. Is it? Yes, it is. It's written on the book. Okay, and it's still a very good book, very relevant in concurrent programming, even if the examples of code you have in it are a little dated now. You can synchronize to prevent race conditions and all this good thing with the synchronize keyword, and we're going to talk a little more about this keyword in a few. And then nothing much happens between 1995 and 2004, which is the release of Java 5 and of the Java Util Concurrent API, written by Doug Lee, the guy who wrote the book that I just showed you. You have a new model for a task, which is the callable. Callable is nice because it can talk to you, it can give you exceptions, and it can also produce a result. The book you want to read is this one, Java Concurrency in Practice. And it's a little sad to say that that's the last book published on concurrent programming in Java. But it's still very relevant. Everything that is in it is perfectly okay, even if the code is maybe somehow a little old-fashioned now because it has been written more than 10 years ago. In Java Util Concurrent, you're not supposed to interact with threads anymore. So if you're still calling new threads in your code, stop doing that. You shouldn't be doing that now, as of 2004. How much was that? 18 years ago? Yeah? Am I doing my math right? Yes, 18 years ago. 19 years ago. 19 years ago. The executor service is actually a pool of threads, and we're going to talk a little more about that. You submit tasks to it. There is one wait list for all the threads you have in this executor service, and the threads are going to take these tasks when they are available and run it, and they give you a future object in exchange that you can query to know if the task is done, if it has produced as a result, or produced an exception. Okay, that's the very simple patterns of this future object. If you want to do some synchronization, you can still, of course, use the synchronize keyword, but you have also APIs to do that, including reentrant lock, and we're going to talk a little more about reentrant locks in a few minutes, and also a bunch of other APIs and classes to do some synchronization, including thread-safe implementations of collections, maps, and this kind of thing. And then there is another big step that is made up to the JDK 7 and JDK 8. We are in 2014, and the Java 8 brings two new elements in the concurrent programming space. The first one is the fork join framework. Maybe some of you already played with the fork join framework? Yeah, some of you. Did you like it? Kind of. Not sure you really liked it. Okay, the fork join framework is built on a new pool of thread. So that's the second model for a pool of thread, which is called the fork join pool, as you know. And the biggest difference between the executor service and the fork join pool is that in the executor service you have one single waitlist for all the tasks, whereas in the fork join pool you have one waitlist per thread. And if a thread generates another task, it will put it in its own waitlist. And if this waitlist becomes full and other waitlists are empty, then the other threads are able to go to this full waitlist and steal some tasks. This is an implementation of a concurrent pattern called work stealing. So fork join pool is able to do that, implements the work stealing pattern. We're going to talk more about it because fork join pool are at the core of the Loom virtual threads. Okay, and the second element is this completion stage API or completable future class. You have one interface and one class. Maybe some of you are using completion stage? No? Yeah? Do you like it? Yeah? Really? Okay, that's fine. I didn't expect that. Okay, so that's a model for asynchronous programming. And the good news is that Loom will probably make this kind of pattern a little old-fashioned. You won't be able to do some asynchronous programming anymore if you adopt Loom. Over all these elements, 1995, 2004, 2014, and we are in 2023, it seems, there's one thing that stays the same, is that once you have given a task to a thread, you have two solutions. Either this task produces a result, which could be void, so it completes normally, or this task throws an exception, so it completes exceptionally, but you cannot, there's no way you can detach this task from the thread you have that is running this task. Okay? There is a relationship between a task and a thread that is completely definitive. You cannot do it. Or you can interrupt the thread, but you cannot do that if you're using executor services, because you cannot get a reference on the thread that is running your task. Okay? And that's very bad, because if your task is blocking for like several milliseconds, then it's blocking the thread. So you need another one to run your other tasks. Okay? And this is exactly what Loom is doing. It breaks this relationship between a task and a thread. So we are in 2023, and you see there's some kind of pattern, 1995, 2004, 2014. It looks like every 10 years something is happening on the concurrent space in Java, right? We are in 2023, 2024, so the train is on time, really. Loom is just on time. Okay, and this is what I'm going to talk about now. But before, I would like to answer a question. Why do we need concurrency? Who likes to write concurrent code? Yeah. All right. So that's maybe 2 or 3 people among this room. Close to nobody. Sorry, you're not nobody, but I mean, it's not many people who do that. Concurrency is complex. It raises race conditions, deadlocks. It can really break your application, right? If you do not do concurrent programming right, what you're doing is that you're breaking your application. It's not just a bug or some process that breaks it. All your application is broken, which is bad. There are 2 elements, there are 2 contexts in which you can use concurrent programming. The first one is called parallel computing. You can think about parallel streams, for instance. You have some kind of big computation to conduct, and you want to leverage all the cores that you have on your shiny new CPU. And for that, you're going to split your big problem into smaller chunks, run every chunk in a thread, and after that, you need to gather all the partial results you have from all your threads into a global result. Okay? This is exactly what the fork join pool is doing, the fork join framework, is doing, or parallel streams are doing. This is about in-memory computation. Loom is not made for that. Virtual thread is not made for parallel computing in memory. Okay? So if you actually use virtual threads to run this kind of computation, you are going to slow down your performances. So don't do it. Okay? Loom is done for I/O. You have a bunch of requests that you want to send to your database or to your REST server, whatever. You are doing input-output computations, and your thread is going to be blocked. And this is exactly the use case that Loom is addressing. That's the problem that Loom is addressing. So Loom is done exactly for that. Okay? If you take a closer look at how I/O is conducted, the first step is to create your HTTP request. HTTP request is mostly a bunch of strings of characters, so you are doing in-memory computation to create all the elements you need to send to your HTTP request. And this is in-memory computation, so it takes some nanoseconds to do. Maybe 10, maybe 100, that's the order of magnitude. All right? And then you send your request on the network. And then you completely change the scale, because now it's in the order of the millisecond. There's a factor of 1 million between a nanosecond and a millisecond. Okay? And then you get your result, you get your JSON object, whatever, and you want to make it a Java object again, or any kind of other language, by the way. It's the same, it's not a Java stuff. And that's some nanoseconds again. So if you look at the life cycle of an HTTP request or database request, nanosecond to prepare the request, milliseconds to get the result, and nanoseconds to process the result. All right? So actually, this diagram is not at scale. If it was at scale, suppose you have 1,000 pixels in the width of the screen, it means that the millisecond is 1,000 pixels, and all the nanosecond, the pre-processing part and the post-processing part, that's 1,000 of a pixel. Okay? So you wouldn't even see it on the screen. Right? So your CPU, if you consider what your CPU is doing, while you're waiting for the request, your CPU is doing nothing. Your CPU is used actually 0.000050% of the time. And that's it. So you bought a very expensive CPU, or maybe you're renting it, and you're basically looking at it, and it's not doing anything. So what's the solution? How many threads do you need to keep your CPU busy, let's say 100% of the time, in that context? Well, the math is pretty simple. You need 1 million threads. Okay? If you have 1 million threads, then okay, your CPU will be kept busy about 100% of the time. Now, what's the cost of one thread? Well, that's precisely the problem. Okay? Because launching a thread takes about a millisecond, and there's a memory allocation of 2 megabytes upfront when you're creating this thread. So if you want 1 million threads, it will take about 20 minutes to launch, between 15 and 20 minutes. Okay? That's 1,000 seconds. And it will eat up, how much? 2 terabytes? Yeah? 2 terabytes of memory? Do you have 2 terabytes of memory on your computer? I don't. So you're limited by that. The number of platform threads you can launch on a regular computer is in the order of 3,000, 4,000, meaning that your CPU will just sit there doing nothing when you're doing this kind of stuff. All right? Because a platform thread is just too expensive. You cannot launch as many platform threads as you need if you want to keep your CPU busy. So what are the solutions that have been brought to the table? Well, all the asynchronous programming is a possible solution to that, at least an answer to that. Completion stage, completable future, async await, mono-multi, all this stuff is about trying to keep your CPU busy while you are doing requests that are doing nothing. Are these solutions good solutions? Well, they're doing the job, kind of. But if you look at them, it leads to code that is probably hard to read, hard to write. Who likes to read asynchronous code? Oh, there were more people who told me that you like to do completable future, actually. It's hard to debug, because when you put a breakpoint somewhere and say, okay, oh, my application is actually running this lambda, right? But the stack trace gives you your framework. It doesn't tell you this lambda has been called by this other lambda. It doesn't give you that. It's impossible to unit test, and it's super hard to profile, or impossible to profile. So from a technical point of view, this kind of solution, I would say it's okay, but it's certainly not the one you want to go with. And that's exactly what Loom is doing. Loom is bringing solutions to this problem. Okay? And I'm going to switch to the IDE because I like to show real code, and because I can also actually show real code. That's supposed to be an IDE. Oh, God. I'm going to try to switch to presentation mode. And I hope it will fix. Yes, it does. Okay. And I'm going to show you how you can create a virtual thread. A virtual thread in Loom is just a thread. We have new methods to run and launch virtual threads. There's a bunch of factory methods that have been added to the thread class. So that's the good old thread class, the class we've been using for years. And we have two factory methods, off virtual and off platform. I'm going to start by off platform. To create a thread that is unstarted, I'm going to pass this task as an argument. Okay. And that's it. That's a thread. Thread T. I'm going to call it T1. Okay. And I can start it because it's a thread. And I'm going to join it, that is, wait for this thread to execute. Join, not start. Thank you. Okay. And I can just copy paste this pattern because I'm lazy. That's a thread T2. And instead of calling off platform, I'm going to call off virtual. And now that's a virtual thread. And I'm going to start it, to join it. And you see that all this task is doing is that it's printing on the console the virtual thread, the thread that is currently running this task. So I'm going to run this code. Hopefully it will work. It's not too complicated as a code, so that should be okay. That's maybe a little big. Can you make it smaller? Okay, and that's what is printed when you run a thread or a virtual thread. So the first thing you need to understand is that a virtual thread is just a regular thread. There is a class called virtual thread in the JDK. It's not public, so you cannot have access to it directly. Okay, you can only create virtual thread through the use of a factory method, right? And you can launch it and execute it and join it exactly as if it was a regular platform thread. So if you have an application that is running on top of regular threads and you want to move to virtual threads directly, it's actually pretty simple. You don't need to change your code. You just need to change the way you are creating your threads. And there's even an executor service for that. And I can show you right now. There is on the executors factory class, there is an executor service which is new virtual thread task per executor. Okay, and if you use this executor service, it's just an implementation of the executor service interface, and it will just create a virtual thread every time you submit a task to it. It doesn't pull anything. It's an empty pull thread. There's nothing in it. Okay, so if your application is based on this kind of thing, you can easily move to virtual thread and see what it gives you if you want to use virtual threads. Okay, and you can see that this platform thread is just the regular thread that we're used to, but this virtual thread, the trace is a little different. It's a virtual thread that is executed on another thread from a fork join pool, and that is called worker 1 in that case. Okay, so virtual thread actually runs on top of a platform thread. It's executed on top of a platform thread. And that's the reason why if you do not do any kind of I.O., stick with your platform thread, because running virtual thread is actually a little more expensive than a platform thread. You need to create this object that is only when you run on top of a platform thread. Okay, so a pretty simple pattern. We are going to play a little more with it. And what I'm going to do is the following. I'm going to create one virtual thread of virtual unstarted, and the task I'm going to give it is this one. Sorry. Shit. Is this one. Okay, if the index, which is 0 or which is just 0 here, is 0, then I'm going to print this virtual thread, and then I'm going to sleep for 20 milliseconds. That's about the time it takes to make a request on the internet. And then I'm going to print this virtual thread again. Okay, so I print this virtual thread, I block it for 20 milliseconds, and then I print it again. That's for only one thread. And I'm going to do that. I'm going to block it again. So I'm going to block it a second time, third time, and a fourth time, because why not? And I'm going to run this code. And this is going to be super annoying. Sorry about that. And you can see that, okay, this virtual thread is actually taking the same platform thread every time. Now I'm going to take more virtual threads, like 10, run the code again, and now you see what is happening. Okay? First, this virtual thread is executed on worker 1, then it's blocked, but when it's run again, it's not on worker 1 again anymore. It's on worker 3, and then 2, and then, 3, and then 2, and then 6. It's like this virtual thread is actually jumping from one platform thread to the other. Can you see that? So when I told you that once you've given a task to a platform thread, there's no way you can detach this task from this platform thread, a virtual thread actually can be detached from its platform thread, put somewhere else, and then when it comes back for blocking, it's actually executed on another platform thread. That's new. Never saw that in Java. Never saw that on any language running on a virtual machine, on the JVM. That's completely new.
So the same task is getting run on different virtual threads?
Sorry, can you say that again?
Same task is getting run on different virtual threads?
No, the virtual thread is always the same, but the virtual thread itself can move from one platform thread to the other, and this is what you're saying here. Okay, you see that the virtual thread is also always virtual thread 22. But the platform thread is worker 1, then 3 again, then 2, then 6. So the virtual thread 22 started on the platform thread, then was moved to another one, to another one, and to another one. So because this virtual thread is actually a thin wrapper on your task, it's just as if your task was executed by different platform threads. Okay? How is this working? Well, at the core of it, there is an object. I'm going to visit this sleep method. Okay. This is the sleep method in the thread class. And you can see that there are two parts. One part for virtual threads. If the current thread is an instance of virtual thread, then I'm doing that. And if not, I'm doing the rest. So it's calling the sleep nano method. Okay, this is annoying. You know what? This is like super annoying. Shit. Okay, so I'm going to visit, there's a call to do sleep nano, and then park nanos, and then yield continuation. I'm still in the sleep method, I'm just visiting part of it. And here you have a call to this line of code, continuation.yield. And this is where the job is done. This is where this mechanic of moving one virtual thread to a platform thread to the other is actually being implemented. This continuation object is just an incredible object, and I'm going to show you how it's working so that you can understand clearly what's going on. It needs a technical object, which is a continuation scope. I'm not going to talk more about it. This is this continuation object there, and you can just call run on this continuation object to execute the runnable that you pass as an argument. So continuation is built on a runnable, and if you can call run on this continuation, it will just run your runnable. If I run this code, it will first tell me that I'm not allowed to use this continuation object, illegal access error. Okay, you cannot access class JDK internal VM continuation scope. JDK internal VM is a package that tells you you should not be using this class in your production code. You're not allowed to. Now, if you really want that, like you need to do a demo, for instance, you need to copy this code, paste it there, basically telling, hey, my name is Jose, I'm doing a demo, please allow me to run it. And now I can run it. And you can see that basically it just executed the code I put here. Now you remember that there was a call to continuation.yield in the sleep method that I just showed you. That takes a continuation scope as an argument. So let me pass you this scope object. Okay, now it's happy. And I'm going to print this again to see what's happening after this call to yield. Okay, so I'm just calling run. Let me run this code again. That's really annoying. And you can see that actually this call to yield suspended the execution of the continuation, of the runnable. Sorry. The second message is not printed on the console, meaning that this yield code stopped the execution of the runnable. You see that? But it's funny because it's like you have a return in the middle of a method, but if you put return in the middle of the method, then the compiler will tell you, hey, this code cannot be executed, and that's a compiler error. And here I have no error, so it's not the same as a return in the middle of the method. Okay? I'm going to print some code there. I am back. Okay? And call continuation.run again. Okay? Let me run this code. And now I see the magic happening. You know what? I'm going to replace this by C2, just to make things more clear. Can you see what is happening there? I'm calling run the first time. That execute the first part of this runnable that is there. Okay, C1 is being displayed on the console. Then yield is called. This block of code, the execution of the runnable is suspended. I am executing the code after the run call again here. Okay? And then if I call run again, the execution of this task continues where it was suspended. Okay? This call to run is not displaying C1, it's displaying C2. So it continues the execution of this task after the yield. Have you already saw that? Did you already see that in Java? No, you didn't. Okay? So this continuation object actually is able to suspend the execution of some code. Okay, and if you call run again on this task can continue its execution normally. And every time something blocks, actually, in Java NIO, for instance, or in this kind of API, it will check if it is in a virtual thread. And if it is the case, it will call this continuation. And this continuation will remove this virtual thread from the platform thread. And then the thread scheduler will call run again once the data is there, if it is some data that you're expecting from the net, for instance, from a network. And it will just bring this object back, this task back to a platform thread that is going to call run again and continue the execution where it was. Okay? Yeah. Sorry, can you just do? Every time you're blocking, you want to suspend the execution of your runnable because it's blocking, it's not doing anything. And it's taking a platform thread. So every time you're blocking somewhere, in all Java NIO, for instance, every time you have a blocking call, you have a check to see if you're in a virtual thread or not. And if you are, then there is a continuation that is created, a call to yield, and a call to run again in the calling thread. Okay?
I have my brain around it. So you're saying that, like, suppose I have like an expensive, time-consuming database call.
Yeah.
And I want to just suspend that.
Yeah.
Move on to another task.
Yeah.
And then come back there. So that could be a use case.
Yeah.
And
if you're in a virtual thread, then the continuation, if you have a Loom-friendly JDBC driver, it will check if you're in the virtual thread, and if it's the case, it will call this code. It will call this code, similar code, and it will just suspend your thread, do something with this platform thread, and then bring this code back again. How is this stuff can be working, by the way? There's only one way to make it work, right? You take the stack of the virtual thread, all the memory allocated to the virtual thread, you need to push it somewhere else, and in that case, it's in the heap. So you put this portion of memory in the heap, you free the platform thread, now the platform thread can run something else, another virtual thread, and when the signal is triggered telling you, hey, the data is there, your expensive database call, the data is now there, then it will trigger that, and the thread scheduler will take this stack back from the heap and install it in a waiting list of the thread it was in first. And if this thread is busy, then another thread will take it because it's a fork join pool, and this is what fork join pools are doing. It will take it and run it on another platform thread. This is what basically, in a nutshell, this is what Loom is doing. And it took 4 years to develop that, to make it work. Okay? And all the Java NIO API have been refactored to leverage that. And I suspect that JDBC drivers are also under refactoring to leverage this kind of thing.
I have a quick question.
Yeah?
I think you may have just answered this, but I just wanted to confirm.
Sure, please.
The example makes good sense. So let's say that our continuation here was waiting for a network call to return.
Yeah?
So we yield.
It's not the continuation, it's the task, it's the runnable.
Okay, so while it's no longer as part of a platform thread, is there a way to know if it's done waiting? Or do you have to just
Yes,
put it
there
back
is.
in?
Yeah,
Oh, wait, never mind.
that's part of the internal API. There is a signal that will tell you, hey, this task is done waiting, so you should take it back.
Okay, so it's not like you have to keep retrying. It knows, okay,
Yeah.
the response is back now. Okay, perfect.
Exactly. That's part of the API. That's part of the API. So the question is, how many platform threads do you need to run your virtual threads? Okay? So we are going to launch another stuff, which is this example. Here, it's basically the same example as just the previous one. I'm going to launch 10 threads. Here, 10. Okay, these are virtual threads that the factory method we've been using just a minute ago. Now we are just sleeping for 2 milliseconds, so it's going to be faster. You know what? I don't even need that. Okay, let me keep it. And I'm going to, every time I do that, instead of printing the result on the console, I'm going to extract the name of the pool and the name of the worker that I have for this virtual thread, because this is what I get, read pool name. And I'm going to add that to concurrent sets that are here, okay? And I have nice regular expressions here to do the job of extracting the name of the number of the platform thread and the name of the worker pool. And I'm going to launch this code and see what it gives. And it's going to be pretty annoying to have this big stuff here. All right, so you see that for 5 platform threads, sorry, for how many okay, I launched 10 virtual threads. 5 worker threads were enough to launch 10 virtual threads. I can jump all the way to 1,000. Run that again. I have 12 cores on this CPU, okay, and 9 platform threads were used to run my 1,000 virtual threads. Well, I can go to 10,000. And you can see that it's basically the same. By the way, it took me 1 second to execute these 10,000 virtual threads, and they are waiting for 2 milliseconds, all of them. So that's nice. 100,000? 100,000 will crash any machine, right? It would not work. Now I'm okay to, I'm still using 9 platform threads, and the time is 2 seconds. 9 is probably some kind of optimization between the number of cores I have, which is 12, and the number of threads that the virtual machine needs to properly run. You know, you have the garbage collector, you have the just-in-time compiler, you have this kind of thing. So it needs to keep some platform threads to run this kind of thing. The garbage collector on the just-in-time compiler are not using virtual threads because they are just doing in-memory computation, so it doesn't make sense to use virtual threads. And you see that 1 million thread takes less than 6 seconds to be created and executed, and it still eats up 9 platform threads. So you can literally launch 1 million threads with Loom on a regular machine. That's a laptop. It's not even a new laptop. It's a 4-year-old laptop. Okay, and there's no problem with that. Try to launch 1 million platform threads on your machine. Go grab a coffee, come back, and restart it, and continue working. Okay, so that's what Loom is bringing. Creating a virtual thread becomes cheap. It's not free, but it's much cheaper than creating a platform thread. Blocking a virtual thread is just the price of moving a portion of memory from the stack to the heap back and forth. So it's not free, but it's much cheaper than blocking a platform thread and having to remove it from the core of your CPU. That's expensive. That's super expensive. So blocking a virtual thread is super cheap. Why would you need to pull virtual threads? Well, it doesn't make sense. Don't do that. It's completely useless. If you need a virtual thread, just create it, use it, block it, and that's it. Okay. Yeah, sure.
So like all this like serverless, like all this like functionality where you're triggered on each message or on timer.
Yeah.
Are they all support virtual threads or still in progress?
Support for what? Sorry.
Support for virtual threads, like all those Microsoft Azure functions or Lambda expression.
You need to ask the question to Azure for that. To be honest, I don't know. I just would like to show you one last thing, which is something that you may come across in your application. Okay, this example is exactly the same as the previous one, but there is a synchronized block in the middle of it. Okay, and I'm launching 1,000 virtual threads, and I'm going to run that. I'm just incrementing a counter, which is some kind of stupid things to do, of course. But you can see that in that case, my virtual thread is not jumping from one platform thread to the other anymore. You can see that? Worker 1, worker 1, worker 1. Which is kind of an issue. You see, I told you that virtual thread, blocking a virtual thread is about moving the stack of this virtual thread from one place of the memory to the other, the stack to the heap. Okay? So there's just one precaution you need to take if you do that. You know that, I don't know if there are people who wrote some C code, maybe back in the days. All right, in C you can have you can create local variables in functions, of course, like in Java, but you can get an address to these local variables. You can write char p equals the address of I, which is an int that you've just declared. So in the C language, you can actually get addresses on stack, which you can't in Java. Okay, so what is happening if you take a portion of the stack and you move it somewhere else, and you move it back, and you run it again, and you have, in this code, you have a variable which is actually pointing to an address on the stack. Well, you're probably in trouble because this address has probably changed in the process. So it means that if your Java code is actually calling some other language code, like C or other languages, C++, which may happen, you can do that in Java, definitely, then you should not try to move the stack of your virtual thread anymore. And this is what is happening here. It's not that there is some assembly code in the synchronized block, but the synchronized block gets an address on the stack to store the references to the thread that are actually waiting on the barrier. Okay? So the Loom is able to detect that, and in that case, it will pin these virtual threads on the platform threads, preventing it to be moved to another place, back and forth. So if you want to use Loom, and you have synchronized blocks in your code, you need to be a little careful, and you need to analyze what's in this synchronized block before doing something. And actually, you need to take a look at that, and your first reflex should be, don't do anything, just check if it's a problem, if it's a performance problem, if the performance gains you were expecting are not there. And if they are there, that's fine, don't do anything. The synchronized block is a problem, the pinning of the thread is a problem, only if in your synchronized block, you're actually blocking your virtual thread. If you're not blocking it, if you're just updating some kind of external state, like an array, a hash map, or this kind of thing, some in-memory computation, means that the thread will just spend a few nanoseconds in the synchronized block. So it's not a performance issue at all. So don't touch it. If you are doing some expensive I/O that will take some milliseconds, then you may consider doing something. And the simplest thing you can do is just replace your synchronized block by your reentrant lock, which does exactly the same, but without this issue of relying on some kind of address or some address on the stack. And if I run the exact same code with a reentrant lock instead of a synchronized block, then my virtual threads are not pinned on my platform thread anymore, and everything is fine. Okay? So if you have synchronized block, just look at the content. If it's in-memory computation, don't touch it. If it's some kind of long I/O blocking stuff, then you may consider refactoring using a reentrant lock. Okay? I would like to show you one last thing, one last demo for virtual thread, which is a Spring Boot demo. Okay, so I have Spring Boot on this machine. And you see this Spring Boot stuff is actually the configuration of the execution service you want to use to create the threads that are going to handle your HTTP requests. So that's the one for, synchronous call, and this is the one for your virtual call. And I'm going to just comment this first. Okay, run this Spring Boot stuff. So that's the default configuration of Spring Boot as of now. Okay, it should be okay. So I'm going to switch to this stuff, localhost 8080. So that's the beautiful page I'm using for demo. I'm a great HTML developer, as you can see. So that's the current thread I'm running in. Okay, you see that's a regular Spring Boot thread, and you see that the thread, you can see that the number of the thread returns to the previous thread. That's 212, 213, 14, 15, 16, 17. And after a while, it goes back to 11, 12, etc. So I have a pool of threads, and this pool of thread is limited in size, and I go back to a previous thread when I'm done with the request. Okay? And I would like to show you a second thing, which is I'm going to generate a basic exception in this request. And you can see that the classical Spring Boot stack trace. So that's my exception method that is generating the exception. And it goes all the way from the platform thread. You can see here I have thread.run, and then all the Spring call stack, and then my service. Now I'm going to run this code again, but this time with virtual threads. So let me stop this, uncomment this. So now what I'm saying is that this Spring Boot stuff is now using this new virtual thread per task executor. So I'm going to run that. That should be good. Let me go back here. I'm going to refresh this page. Yes, you're here. Great. Now you can see that the current thread is a virtual thread. And I refresh this page. You see that it creates actually a virtual thread for each request forever, never goes down, as it was the case for the platform thread I was using just a few minutes ago. And if you check the stack trace, here, same kind of stack trace, that's the call of all the Spring code. But you can see that this time, it's not starting at thread.run as it was the case, but continuation.enter. Okay, so that's this continuation object that is actually executing my code, and that's the reason why it can be suspended and move from another platform thread. Now in this context, platform threads are completely invisible. You cannot see them anymore. They are just installed on each core of my CPU. They are never moved, and it's just the dance of the virtual threads on top of them that will handle all my requests. Okay, so that's a regular version of Spring Boot 3 dot something, that hopefully will probably become virtual thread friendly by default once virtual thread make it as a final feature in a JDK. Well, I can tell you, I don't think it's the exact last one, because I didn't upgrade exactly. This one.
I'm asking which version of the Java is going to become final.
Oh, which version of Java is going to have virtual thread? So for the moment, virtual thread are a candidate final feature for 21. So if this JEP makes it through all the process, and that should be done in May or June, then it will be a final feature of the JDK 21. But it's not done yet. Okay, so I'm not telling you that it's going to be. I am telling you that it's on track, which is the fact. Yeah, question?
This is an incubator feature in JDK 20.
So, virtual threads are a preview feature. A structured concurrency and scope value are incubator APIs, and there'll still be incubator APIs in a JDK 21. There's no plan to have them as final features. Other questions?
You had a slide at the beginning that had the startup time, memory consumption, and context switching for a platform thread.
Yeah.
Do you have the equivalent numbers for?
It's about 1,000 times faster and consumes 1,000 times less memories. So the startup time is in the order of the microseconds, and the memory consumption as of now is in the order of the 100 of kilobytes. Now there are optimization underway to reduce that even further by a factor between 2 and 10. So in the end, it will be in the order of 10 kilobytes. So that's very, very few. Yeah?
Just trying to see if I understood it correctly. This means that you can write your controller as you would normally do, but you get a virtual thread instead, right? You can
Exactly.
do any blocking calls.
Exactly.
And does debugging work like linearly through your code then as well?
Yeah, absolutely. There's no change. I mean, you don't even know you're in a virtual thread. It's there for you, and that's it. I just would like to show you two elements. That's nice because I just saved so many slides by just showing you code. You prefer code than slides, right? Yes, of course you do. I just would like to give you a quick hint about structured concurrency, because odds are that you're not going to interact directly with virtual threads. Actually, if you're a Spring Boot developer, this is not what you do, right? But structured concurrency really is going to be a game changer when it makes it as a final feature. So I'm just going to show you a very quick example, which I call the travel agency example. So you are just trying to build a travel page, right? And you need to query two servers, a quotation server and a weather forecast, because it's nice to tell people, hey, you should go there. The weather will be fine. You should go to Paris. There are no strikes currently, and the weather is just super sunny. Okay? If you want to handle this problem using completable future, this is the kind of code you are going to write. Okay? Do you like it? No, you don't. Neither do I. I wrote it. Okay? And it's even a simplified version of the real problem you want to solve. Because the real problem you want to solve is this one. You want to query several quotation servers to get the best price, and several weather forecasts to get the first weather as fast as you can. All right? So imagine writing this code to do that. Good luck in doing that. That's going to be super complex. That is the pattern that is offered to you by structured concurrency. Create a scope object, fork your tasks, your querying tasks, join, wait for the result, and then program some kind of first weather method that will just give the first weather. For the quotation server, it's the exact same kind of code. Fork. You see, you move from a case where when you want to fork more tasks, you are just calling more callbacks, to a case where you are just chaining calls. This is purely imperative code. Super easy to maintain, super easy to read, understand, update, even unit test. Okay? If you can create a scope for your travel page, that's the same. It's always the same pattern. Always the same pattern. Okay? Inside, this fork method actually produces a future. You can process this future within the scope object itself. There is a callback method for that, and that's probably the most complex code that you're going to write to handle this future object. It's just a switch, 4 branches, because there are 4 states for the future object, and you do whatever you want with the result. Super simple, super slick. And the best quotation method that I just showed you is just this one. You accumulated your quotations in a collection, and then you need to take the mean. That's just Java 8 basic stream code that you've been written for 10 years now. Okay? So that's I would say the structured concurrency APIs. There is another API that is also underway, which is the scope value, which is a replacement for thread local variables. Thread local variables are working with virtual threads. So if you are using thread local variables in your application and you move to virtual threads, it should work out of the box. It's fully backward compatible, but you can do much better using scope local variables. So this is also something you need to check out. All right. Structured concurrency in 3 words, and there are actually 4. Easy to read, easy to test, easy to debug, and easy to profile. Okay? So if you want to check that out, there are many resources on YouTube. I recorded several videos on that to show you how it's working, and you can also check the tutorials available. And that's it. Thanks for your attention.